Okay, welcome, period 6. I mentioned that because it was a half day, we had only 30 minutes instead of 60 minutes that you would be watching a video. This is stuff that I covered in the live Zoom call in periods 3 and 4 on Thursday, but we didn't get a chance to do it, so we're going to keep the classes in sync, or we're going to try to. I think I mentioned at the very end of our Zoom call on Friday that solving systems of 2 equations in 2 variables is kind of easy, but once you start solving systems of 3 equations in 3 variables, if you want to interpret what you are doing geometrically, then you have to envision what's going on in 3 dimensions. And that, in fact, a linear equation in 3 variables can be interpreted as a plane. Okay, so in order to get the necessary background information so that we can understand planes, you have to go through this entire subject of the 3D coordinate system and 3D vectors and equations of planes. You did this last year in the spring with Mr. Kirk, but okay, we should review it because it's kind of hard, and I think it was the last thing that you did at the end of last year, and perhaps you forgot. And I didn't put it anything from this unit on the summer packet because every year I review it in class. So I'm going to do that now also. Okay, so this is all review. This should be something. This should be things that you learned last year, but I think it's worth doing it again. Okay, so there's the 3D coordinate system. And if we go into 3 dimensions, then we take our normal 2-dimensional coordinate system and we think of that as being on the ground. And so we let the z coordinate refer to how far up we go. Here, I've put the origin here. It's more fun to do this sort of live in a classroom where I can kind of point to a corner of the room and call that our origin. But okay, anyway, here we are. With this picture, the x-axis is kind of coming out at the board, and the y-axis is going this way, and the z-axis is going up, and the dotted lines are just the continuation, the negative axes. So the solid lines are the positive ones. Okay, I think you know this already. If this were, then you have the xy plane. The xy plane is the plane formed by the x and y axes, so sort of on the ground here. The yz plane is kind of this back wall, and the xz plane is the plane formed by the x-axis and the z-axis. Okay, so that's 3 dimensions. I think you know all this already, basically. And then we have 3-dimensional vectors. And a 3-dimensional vector, such as, so you have I, let's not forget, is the unit vector that points in the positive x direction and has magnitude 1. J is the unit vector in the positive y direction of length 1. That's what unit vector means. And k is the unit vector which points in the positive z direction and has magnitude 1. So when I want to talk about a vector, I can refer to that vector as 5i plus 6j plus 7k. Say, if I want to. This is kind of a little bit of an old-fashioned way of doing it. This means, go over 5 in the x direction, up 6 in the y direction, and up 7 in the z direction. That's a vector. Okay, that's fine, but it's maybe more common to write the vector in the form 5, negative 6, 7. This is called component form, and these numbers are the components of the vector. The x component, the y component, and the z component. I guess I wanted to do like that. Okay, good. That's just some sort of simple vocab. And I think Mr. Kirk used both of those forms last year. Okay, so the thing I did with periods 3 and 4 on Friday was I reviewed the dot product. All right, what is the dot product of 2 vectors? Well, it's a helpful thing. It's a thing really kind of inspired by physics, I suppose. Sometimes you have 2 vectors and you want to know the amount that one vector is pointing in the direction of the other. And so it's related to sort of projections and stuff like that. But okay, I'm just going to give the definition. The definition is that if I take vector u and vector v, then the dot product of those two vectors is the magnitude of u times the magnitude of v times the cosine of the angle between those two vectors. And this works in 2 dimensions, 3 dimensions, or whatever. Number of dimensions, actually. What's the sort of picture here? If I have a vector u and I have some vector v, then what you sort of do is you kind of project in the and this is the angle between them. Then if you take sort of this vector here, this is kind of maybe don't even think of it as a vector. Just think of what is this sort of length. What is this purple length? Well, it's the magnitude of u cosine theta. And so what you're really doing when you're taking the dot product of two vectors is you're multiplying the length of one vector times the length of the projection of the other vector onto that first vector. And this is useful for things like work. If v is the displacement vector and u is kind of a force vector, then work is force times distance, but only the force in the direction that you have been displaced is relevant for work. Okay, good. What can we do with this? Well, there's like a theorem, right? And the theorem, the big theorem on dot products is that if you take the dot product of two vectors, let's say they're two 3-dimensional vectors, and the first one has components x1, y1, z1, and the second one has components x2, y2, z2, then when you take the dot product of them, there's this just really cute little formula, which is you take the product of the x components plus the product of the y components plus the product of the z components, and that gives you the dot product. And in my opinion, it's totally not obvious why this formula is correct. And so there is a proof of this. The proof maybe takes only 5 or 10 minutes, but I'm not going to do it right now. But if you want to remind yourself of the proof, hopefully you did it last year with Mr. Kirk. But if you want to be reminded of the proof or given a hint on how to try to do it yourself, the idea goes like this. You just make a triangle here. And if this is vector u and this is vector v, then this vector must be u minus v, because u plus u minus v is vector v. And now you just apply the law of cosines. So apply the law of cosines to this triangle. So you just write out u in component form, you write out v in component form, you write out u minus v in component form, and you compute the magnitudes of all of those using the 3-dimensional Pythagorean theorem, and it just all kind of works out. Okay, what's the takeaway? So why is the dot product so useful besides just for physicists? Well, for one thing to notice is that it's just really easy to compute dot products. It's just a simple number of multiplications and additions. So it's nice and easy and fast to do. But the other thing that's good about it is that we can find theta easily. So if you give me two vectors, using the dot product, I now have a way, together with this theorem, I now have a way to find the angle that those two vectors make with each other. Because this is just easy to compute using this formula, and the magnitudes are easy to compute, so I just divide and I take the arc cosine. This is something you did last year, found the angle between two vectors. So that's nice. And even another takeaway is that if you take the dot product of two vectors, which are not, let these be not zero vectors, but you get 0. Well, looking back at the definition of dot product, the only way for the dot product of two vectors to be 0 is if the cosine of the angle between them is 0. and cosine is the x-coordinate, so the only time that the cosine is 0 is when the angle is 90 degrees. So if the dot product of two vectors is 0, then it must mean that the angle between those two vectors is 90. And conversely, of course, if the angle between those two vectors is 90, then cosine 90 is 0, so the dot product will be 0. Therefore, the dot product is kind of a test of whether two vectors are perpendicular. Okay, good. Let's do sort of one thing now, and that is, let's find the equation of a plane. Okay, so suppose I want the equation of a plane. How am I going to do this? Well, first of all, let's remember everything we learned in Algebra 1 about the equation of a line. And if we kind of think about the equation of a line, well, okay, you have some y-axis and some x-axis, and you have some line, and the line is just kind of doing its thing. So I want to know the equation of this line. Categorizing lines is pretty easy. Lines that are in two dimensions, because there are really only two questions to ask. There's the question of sort of, in what direction is the line tilting, is one question we might ask, and the other one is, where is the line? So there is some sort of angle that the line is pointing at or something like that, and then there's sort of where it is. And if you tell me those two things, then you've told me everything I need to know. In other words, there's this thing called slope, and then there's sort of the position. So the slope because two-dimensional lines that are in the plane are so simple, the slope can be represented with a single number, and that single number is just the ratio between the change in y and the change in x in that line. So if you give me the slope and you give me a point, then I can find the equation of that line. All right, well, when you move to 3 dimensions, everything gets a little bit harder. Okay, this works better live, of course, anyway, hopefully this is coming through a little bit on this video. It's kind of hard to do 3-dimensional demonstrations because I can't see what's on the camera. Here's a plane, and actually I think maybe I can see myself. It's a very professional thing we got going on here. So here is this plane, this whiteboard I'm using as my plane, and I want you to kind of feel that in order, just like with lines, with planes, there are 2 things that I need to know in order to know the equation of the plane. I need to know sort of like the direction, the tilt of the plane, so to speak. How is the plane oriented? What's the orientation? I'm using sort of vague words. And then I need to know sort of where it is, right? Once you tell me how the plane is like pointing, well then there's still an infinite number of planes that could all be pointing in the same direction. Okay, well how can I capture the sort of tiltiness of the plane? Well, I'm sort of shaking it around in all directions to sort of convince you that because there are sort of multiple degrees of freedom, it's no longer going to be the case that a simple ratio of 2 numbers will be able to capture that. In other words, I'm not going to be able to capture the tilt of a plane with just a single number, which for lines is just the slope. But here, one number is not going to do that. There's just too many different ways the plane can be moving. Okay, so what's the solution to this problem? This is all review. You did this last year. The solution to this problem is to use a normal vector. A normal vector is just a perpendicular vector. And for any given plane, I can describe the direction that a 3-dimensional vector is pointing, which is perpendicular to that plane. And I want you to sort of feel that once you tell me the particular direction that the normal vector is pointing in, then that sort of locks the plane into that particular orientation. Okay, so before we even do any sort of algebra or anything, I want you to feel that geometrically it should suffice to describe a plane if you tell me the direction the plane is pointing in and where the plane is. In other words, if you give me the normal vector to a plane, and you give me one point which is on that plane, from that I should be able to find the equation of the plane. Okay, so let's do it. I don't like looking at myself during recording. Okay, so let's do it. Well, here we go. Here's just my example I just made up with just some sort of arbitrary numbers. So suppose that the normal vector to this plane is the vector 3, -5, 4. Is a normal vector, and that point P, which is 6, 7, -2, is on the plane. Okay, and based on our previous conversation, this should be enough information to find the equation of the plane. The normal vector and a point on the plane. Alright, let's do it. I will draw my three-dimensional coordinate system just for context, just to remind myself that I'm doing everything in 3D. But I'm going to do this kind of generically, so I'm not going to attempt to draw this plane like where it's supposed to be or anything. Okay, so here's my sort of generic plane just floating out there, and there are two things I know about this plane. I know that there's this point, P, and this point P has coordinates 6, 7, -2, and then I know that there's this normal vector. Okay, well, what should I do now? Well, now I need to sort of think, well, okay, what does it even mean to come up with the equation of a plane? We talk about this kinds of thing all the time, the equation of a line, the equation of a plane, the equation of a circle. What does it mean when we call some sort of piece of algebra the equation of some geometric object? And the answer is that this piece of algebra is supposed to sort of capture the geometric object, in the sense that this piece of algebra is kind of a test. It tells you, for a given point, whether that point is on that object or not. So I need some algebraic fact that holds of all the points on this plane, and only the points on this plane. So what I need is like a point, a generic point. And so the next sort of move here is to pick a generic point. I'm going to call this point Q, and I'm going to give it coordinates x, y, z. And the only thing I know about this point is that it's on the plane. Okay, maybe this is sort of obvious, and this whole thing is reviewed to you, so maybe this is totally clear. But what I've now just done is kind of a high-level idea, which is by picking this arbitrary point, x, y, z, now that's on this plane. Now if I can tell you one thing that's true about this point, then I will have told you something which is true about every point on this plane. And that's just what the equation of a plane is. It's a fact which is true about every single point on the plane. Alright, now, when I did this live on Thursday, I asked the class, and I got some good answers, what is true about this point Q? And what's true about this point Q is, well, okay, it's in the plane, but P is also in the plane. And so if P and Q are both in the plane, then so is the entire vector PQ in that plane. And now I reach for the other piece of information that I had, which is the normal vector. And I say, okay, this normal vector is perpendicular to this vector PQ. So I want you to sort of feel that, right? That because the normal vector is perpendicular to the plane, it's perpendicular to every line in the plane. And so I'm going to sort of write that down now as kind of the one piece of information that I know for sure. I know that this normal vector is perpendicular to the plane PQ. And just to be clear, that's true for every Q. So I want you to now use your imagination and let this point Q sort of roam freely all through the plane in all different places. No matter where that point Q goes, as long as it stays in the plane, it will always be true that vector PQ is perpendicular up to plane N. And the converse also holds, right? If any vector PQ is perpendicular to the normal vector, then that point Q must be in the plane. Okay, and so all I need to do is just to describe what's true about all these points x, y, z, which have this property. Okay, so just pushing on here, I now reach for the thing that we just reviewed 10 minutes ago, the dot product. So if this is the case, then the dot product of these two vectors must be 0. And so vector PQ dot vector n has to be 0. So now I've sort of rephrased this geometric relationship as a kind of algebraic relationship. And well, what is vector PQ again? It's just the displacement vector from point P to point Q. And so the x coordinate changes by x minus 6. The y coordinate changes by 7 minus y from P to Q. And the z coordinate changes by z plus 2. And if I dot that vector with the vector 3, negative 5, 4, that should give me 0. Okay, what does this, so what have I accomplished? Well, I think you see now, right? Now I can just reach for my theorem about dot products. And computing the dot product of two vectors is just simple. It's just 3x minus 6 plus, or rather, negative 5, 7 minus y, and plus 4 z plus 2. And that, those should be parentheses, that has to be 0. Okay, and now I've succeeded, because I now have just this simple line of algebra, which is in fact just a bunch of numbers and variables, and what's true about this, put a happy face because I'm sort of, I could be done, is I have made a statement, and if there is any x, y, z that satisfies this statement, then it must be on this plane. And that's what it means to find the equation of a plane. And if it's on this plane, it must satisfy this equation. Okay, so normally people clean it up a little bit, and they do 3x minus 18 minus, okay, plus 5y. Have I done something wrong? Oh yeah, sorry, that should be y minus 7. I don't know why I reversed those. So that's so sorry about that. So minus 5y plus 35 plus 4z plus 8. Yeah. Okay, and if I now do a little bit of arithmetic, then I get 3x plus, no, minus 5y plus 4z, and let's see, 10 plus 25 equals 0. And now this is hopefully starting to look a little bit more familiar. We say that this is, you know, the equation of the plane. Okay, and I think that you did something very, very much like this. Hopefully you did this almost this exact same lecture in the spring with Mr. Kirk. And I think this should have been a little bit maybe surprising to you. It's not obvious, I think, to someone who has not been through this argument, it's not obvious that this algebraic equation here in this black rectangle should necessarily geometrically be interpreted as a plane, but it is. Okay, the last thing to say is that I notice something here, which is that there are these coefficients, 3, negative 5, and 4. And I have seen those coefficients, 3, negative 5, and 4, before. They are these same three numbers. the components of the normal vector. And of course that's not a coincidence, because these numbers came from this step, and this step came from taking the dot product with the normal. And so in fact, this is always going to happen. And so the first time ever that you do this, maybe the second time, the third time, you do this entire process out until you understand it. But in the future, there is a short way. And the short way, the sort of shortcut to doing problems like this, is to just know that this is always going to happen. And therefore, if I were to do this entire problem over again, the short way, I would just see that the normal vector is 3, negative 5, 4, and I would immediately skip to 3x minus 5y plus 4z, and the only thing I don't know is the constant. In other words, the coefficients of the x, y, and z variables, respectively, in the equation of the plane is just the components of the normal vector. And knowing that, and knowing that this point 6, 7, negative 2 is on the plane, I can just stick in 6, 7, negative 2, this is the short way, and just solve for what d would have to be in order for that point to satisfy this equation, which it must. And so you get 10 minus 35 is negative 25, and so d has to be 25, and therefore you would just go right there. Okay, so in other words, you don't have to go through this entire logic every single time once you get it. Okay, that was a short review on the three-dimensional coordinate system, the dot product, and finding the equation of a plane. Period 6, we are now caught up with period 3 and 4. More videos coming. Goodbye.